In this video, we will discuss waiting line problems. Waiting line problems are also called queuing problems. In the service industries, the wait line management is a critical issue because a large portion of customer satisfactions come from their waiting experience. It is worth to note that waiting line problems do not exist externally to the customer only. Internally, it is also an important task. The main difference is that internally, it is easier to estimate the value of lost time for employee. However, externally, it is much more difficult to value customers' time. So why do people have to wait? The main reason that waiting time occurs is randomness. Customers arrive randomly, and the service time required for each customer is also available. The higher the availability, the longer the wait. If there is no randomness, then nobody has to wait, so long as the service rate is much higher than the customer's arrival rate. This graph can explain what happens in an easier way. Because people will try to arrive to the service station randomly, sometimes we will have a lower number of arrival, and sometimes we will have a much higher arrival. However, our capacity is usually fixed. Hence, whenever the number of customers in the system exceeds the service capacities, the system will congest and people will have to wait. So, how do we measure the cost of waiting? The cost of waiting can be categorized into two. The first one is quantifiable cost, which includes salaries paid to the employee, space taken by the waiting area, or even loss of business when customers leave due to a long wait. The second type includes those hard to quantify. For example, loss of future profit due to unhappy customers, or even loss of social welfare, such as patients who has to wait in the hospital for their ER bed. Generally speaking, we can manage the waiting line in several different ways. For example, we can ask customers to join the different lines based on the service they requested. This may not necessarily reduce the waiting time, but it can make the line shorter, which is a pretty big deal for many customers. We can also train the server to be more friendly to improve the overall experience. We can even inform the customer what to expect by showing them the expected waiting time. Or we can try to divert their attentions during the wait by offering the big screen TV, comfortable chairs, or even coffees. Or we can encourage customers to come during a less busy time using the appointment system or monetary incentive. For example, restaurants often try to use happy hours to encourage customers to go to the restaurant at the less busy hours. If we want to reduce the waiting time, the main trade-off would be the capacities. Yes, we can reduce the waiting time by adding more servers or hiring more people, but capacity is often expensive to add. Now, let's talk about the queuing system components. In general, we consider a system from the moment when the customer walks into the store until they leave. Customers arrive to the store follow arrival distributions, which is often defined by the inter-arrival time or arrival rate. Inter-arrival time refers to the time between consecutive arrivals. For example, we can say customers arrive to the store every 10 minutes on average. Arrival rate refers to the number of arrivals in the unit time period. For instance, we can say that on average, we got 10 customers every hour. Speaking of arrival, one of the most commonly used arrival distribution is Poisson distributions. It can be defined with one parameter, and we often call it lambda. When we have Poisson arrival, it means that the number of arrivals will follow Poisson distributions with the arrival rate lambda. Or we can say that the inter-arrival time follow an exponential distribution with mean equal to 1 over lambda. When we have Poisson arrival, it means that we can use the formulations on the bottom to calculate the probability of having n arrivals within the next t unit of time. Let's take a look of a couple examples to see how it works. Now let's take a look of a very simple example. The customer arrives to your store every 5 minutes, and what is the probability that you have 3 customers arrive in the next 20 minutes? So in order to do the calculations, the first thing we need to identify is the arrival rate, lambda. And since here it's mentioned that the customer will arrive to your store every 5 minutes, so we know the inter-arrival is 5 minutes. And from the previous slide, you probably will know that the inter-arrival can be denoted by 1 over lambda. So in this case, 1 over lambda is 5 minutes. That means our arrival rate lambda is 1 over 5 per minute. So every minute you will get 1 over 5 customers arriving to your store. And we want to calculate what's the probability that you have 3 customers arrive in the next 20 minutes. And we know we can calculate the probability of having an arrival for the next 10 minutes based on the formulation right here. And it will be lambda times t power of n multiplied by exponential negative lambda times t divided by n factorial. Okay, so if we want to calculate the probability that you have 3 customers arrive in the next 20 minutes, basically we want to calculate P20 and 3. And we just need to plug in all the numbers. We know lambda is 1 over 5. And our t is 20. Our n is 3. We have exponential 1 over 5 times 20. Everything divided by 3 factorial. So what we have here is 64 times exponential negative 4 divided by 6. And the answer will be 0.1953. So the probability that you will get exactly 3 arrivals in the next 20 minutes will be 0.1953. Now, let's take a look at the next example. The customer will arrive to your store every 2 per hour and you follow a Poisson process. Suppose that your store is to be closed in 30 minutes and it takes at least 40 minutes to serve 1 customer. Given that your store is empty now, what's the probability that you will not be able to close the store on time? So let's see what does that mean. Suppose this is where we are now. And within 30 minutes, you plan to close the store. Imagine there's 1 customer arrive somewhere here. We know it takes at least 40 minutes for you to serve that customer. Okay? Maybe there's another customer arrive right here. Again, it will take at least 40 minutes for you to serve that customer. What does that mean? It means that as long as you are getting customer within this 30 minutes range, you will not be able to close the store on time. So it can be 1 customer, 2 customers, or even 10 customers. So let's try to do the calculation right here. First, we know that the customer will arrive at a rate of 2 per hour. So we know lambda is equal to 2 per hour. But if you read the problem description carefully, you will notice that for every durations we are talking about here, the unit is in minutes. So the first thing you want to do is to convert this to minutes. That means for every 1/30, that means you will receive 1/30 customer per minute, and that's the lambda that we are going to use. So the next thing we want to do is to find out the probability that you cannot close the store on time. So how can we do that? We know the probability that you can close on time will be all the possibility that you are getting customer within the next 30 minutes. So it will be P30 plus P30 of 2, P30 of 3, and even P30 of infinity. Okay? But if you want to plug in all the formulation right here, you probably will notice that it is almost impossible for you to do the calculations because we have infinity terms that you need to take care. And so this is what we are going to use. If you still remember what you learned in probabilities, you probably will notice that suppose we have a sample space. In this case, we have only 2 partitions. One is that you close late. The other one is you close on time. And the sum of these 2 will be equal to 1. So you either close late or you close on time. In other words, if we want to calculate the probability that you cannot close on time, basically it means that I can calculate the probability that I use 1 to subtract the chance that I close the store on time. Okay? Then what would be the possibility that you can close the store on time? That would be I'm not getting any customer in the next 30 minutes. So it is equal to 1 subtracted by P30 of 0. Then you just need to plug everything into your formulations. I have 1 here, subtract by P30. That means I have 1/30 times T power of 0 times exponential negative 1/30 times 30. Everything divided by 0 factorial. Okay? And this term will goes to 1 because when you have power of 0, it is 1. Similarly, if you have 0 factorial, that means it is equal to 1. So basically, what I have here is 1 subtracted by 1 times e negative 1 divided by 1. So this is equal to 1 subtracted by 0.3678. And my answer will be 0.6322. Okay? So the probability that I cannot close the store on time will be equal to 0.6322. Alternatively, you can say that the probability that I can close the store on time will be equal to 0.3678. Let's try another example. Your interview is scheduled at noon, and you arrive to the taxi station at the airport around 11 in the morning. It takes exactly 40 minutes from the airport to the interview locations, and there are 2 travelers in front of you at the stations. And the dispatcher tells you that the taxi will arrive about every 5 minutes. What's the probability that you will not be late for your interview? Okay, let's try to see the timeline right here. 11 in the morning, you arrive at the airport. Your interview will be at 12. This is your interview. Okay, and it takes 40 minutes for you to arrive from the airport to the interview location. In other words, if I don't want to be late, then the latest time I need to be in the taxis will be right here. It takes 40 minutes for you to travel from the airport to the interview locations. So I need to be in the taxis no later than 11:20 in the morning. Okay? Then I also know that at the taxi stations, there are 2 people in front of you, and you are the 3rd person right here. So if you don't want to be late, it means that within the 20 minutes right here, we need to have at least 3 taxis arrive to the taxi stations. Okay? Now, let's figure out the lambda first. We know the taxi will arrive about every 5 minutes. So the inter-arrival time will be 1 over lambda. That will be equal to 5. So this can be translated into lambda. The lambda will be 1 over 5. And this is 1 over 5 customers, 1 over 5 taxis per minute. Okay? Now, if I don't want to be late, I know I need to calculate all the possibility that you are getting at least 3 taxis within the next 20 minutes. So it will be P23 plus P24 plus P20 infinity. Okay? And similar to the previous questions, we know this is very difficult to calculate, so I can use a different rule. I want to use 1 subtract by the probability that I will be late. Okay? So under what conditions you will be late? That will be a case where you get less than 3 taxis within the next 20 minutes. So basically, there are 3 possibilities. 1, subtract by in the next 20 minutes, we are not getting any taxis. And with the next 20 minutes, we only get 1 taxis. Or within the next 20 minutes, we are getting 2 taxis. Then you just plug in all the number. I have 1 and subtract by, let's see right here, it will be equal to 4 power of 0 exponential negative 4 0 factorial. Subtract by 4 power of 1 exponential negative 4 and 1 factorial. Subtract by 4 squared exponential negative 4 and 2 factorial. And the final answer will be 0.7619. Okay, so 76% of chance that you will not be late. Similarly, we need to define the service time distribution in a QE system. We will talk more about that in the next video.